Hello, welcome to our semiconductor education program. This is Vincent Chang. Today we are going to continue our study on Intrinsic Semiconductor. Intrinsic Semiconductor Part 2. Energy bands and bandgap. Energy bands and bandgap. So before we dive into the energy band diagram, let's quickly review what we learned before. So it's about bond model. So at absolute zero temperature, and then on your left-hand side, you see the diamond structure, the two-dimensional scheme of the diamond structure. And then covalent bond, valence electron. So valence electron, so a pair of valence electron forms a covalent, so-called covalent bond. So on your right-hand side, so when the temperature increases to, as for example, room temperature, and then what? Because the lattice vibration, the bond will be broken, and then generating, so the electron is kind of escape out of the covalent bond. So become a free electron, become a conduction electron. And when the electron leave the covalent bond, at the original seat, an empty seat will be left in the covalent bond. So creating the electron hole pair, or conduction electron hole pair. All right, so the red dot outside the covalent bond is called the conduction electron, and then the empty spot within the covalent bond is called the hole. So the hole can be treated as a positive charge carrier. So semiconductor material by nature is composed of two types of charge carrier. The negative charge carrier is called conduction electron. The positive charge carrier is called the hole. So this is the real space. You see the diamond structure, all right? So it's the real space, So now we're gonna transform from the real space to so-called energy space. In this space, in the real space is the x, y, z, right? But in real space, I said it's x, y. But in energy space, this is not z. This is energy, all right? This is energy. This is low energy. This is high energy. So now we are in the energy space. The vertical axis represents the electron energy, not hole energy, electron energy. All right. So at high, here, if up here is the high electron energy. If down here is the low electron energy. For semiconductor materials such as silicon, there are two bands. The low band below EV, the upper band above the EC. So the low band is called valence band. And then the upper band, this is a little bit hard to, because it's kind of abstract. I don't know if you have ever learned the Fourier transform. So it's kind of similar, because in the time domain, it's real, right? Because we live in the time domain. We are not living in the frequency domain. So if you do the Fourier transform from time domain to frequency domain, sometimes you get struggling, right? So same thing here. So this is not the real space, but the energy space. So at the lower band, but if you want to get some insight, you need to learn this in the semiconductor, all right? So I try my best to help you understand. So at the lower band, it's called valence band. And the upper band is called conduction band. So the upper band, so two bands. So what does that mean? What does that mean? If you are an electron, you have two choices. You either stay in the valence band or you go into the conduction band. So in energy space, if you ever learn the modern physics, and then you solve the Schrodinger equation and try to get the eigenvalue, the energy, and then it's kind of the concept of quantize, right? It's similar to what we solve the hydrogen atom model. The energy has to be quantized. So in silicon, you have two choices. You either stay in the valence band or you go up to the conduction band. If you want to exist, an electron want to exist in the semiconductor material, then you have the two choices. You either stay in the valence band or you go into the conduction band. So in the middle, in between, there's no solution. There's no solution. It's the forbidden area. So this area is called forbidden band. And the height of the forbidden band is called the band gap. It's called the band gap energy. In other words, it's the distance, it's the energy between the conduction band minimum, EC, and the valence band maximum. The energy between the conduction band minimum, which is the EC, and the valence band maximum, which is the EV. And energy band gap, the band gap energy is very, very important characteristic parameter for a semiconductor material. So different material will have the different band gap. All right, for example, gallium arsenide is the 1.42 electron volt. And for silicon, at the room temperature, it's the 1.12 electron volt. All right? So at absolute zero temperature, this is what happened. So at absolute, I just tell you the result, the outcome, the conclusion, all right? The summary, I should say summary. So here's the summary at the concept. At absolute zero temperature, the valence band is fully occupied. So when a valence band is fully occupied, the conduction band is empty. All right? So in other words, if you travel in the conduction band, try to find any electron, you find nothing. You will find nothing. So no electrons show up in the conduction band. What does that mean? What does that mean? That means at absolute zero, there's no conduction ability, insulator. So the semiconductor behaves like the insulator. But when temperature increases, for example, when the temperature increases to the room temperature, it's increased to the room temperature, then what? Then the valence electron get the energy out of the thermal. All right? So at room temperature, so because the valence electron receive the energy, receive the thermal energy. So once the valence electron receive the thermal energy, and then at the upper level of the valence electron can jump. All right? So jump to where? So the energy has to be sufficient. If the energy is sufficient, then can jump across the band gap, then reach the conduction band. Then the electron can stay there, right? So when the electron jump into the conduction band at original home, it's going to create a space. All right? It's going to create a space. And then, I just try to think about, try to help you understand this. Hold on. This is the water bottle, right? This is the water bottle. So just imagine, right? So there's a bubble. There's a bubble on the top of the water bottle. And full of the water. So the water represent what? It's the metaphor for, the bottle is the metaphor for what? For the valence electron. And all of a sudden, if I flip the bottle, now what would you see? You see? You see the bubble is going to go up, right? But who was moving? Who was actually moving? The water was moving, right? But are we crazy enough to try to analyze the behavior of the water moving? No, we just said the bubble going up, was going up. So in the same way, when the valence band, if there's a vacancy, and then it will attract the surrounding valence electron to occupy the seat. Okay, all right? But it's a very complicated process to describe the valence electrons occupy seat behavior. So instead of focusing on the valence electron, we focus on the empty spot. We track the trajectory of the spot of the empty seat. And that empty seat, that empty space is called the hole. It can be described as a positive charge carrier. But anyway, so now at the room temperature, electron hole pair is created. And another electron hole pair is created. And another. So this process is called what? In the real space, we said this. This is lattice vibration. And the bond is broken, creating the electron hole pair. But in energy space, we simply say thermal generation. So generate what? Generate electron hole pair. Get it? So let me just quickly sum up, do a contrast between the bond model and the energy model. So here's the bond model. On your left-hand side is absolute zero. On the right is room temperature, right? So let's do a contrast. At absolute zero, in the language of the real space, in the real space language, we said, this is it, right? So all the electrons in the bond. So no bond is broken, right? So every seat is occupied. So if you travel in the crystal, you see no electron is transporting, no conduction electron, insulator. But in the language of energy band, what would you say? You said the valence band is filled, is fully occupied, and conduction band is empty, insulator. All right, get it? So the contrast between the real space on your left and the energy space on your right. So now, at the room temperature, then something changed. Because the lattice vibration, the bond, will be broken, creating an electron hole pair in the real space. But in the energy space, then the valence electron receive the thermal energy jump into, if the energy is sufficient enough, to jump into the conduction band, creating the electron hole pair. All right? The particle in the conduction band is called the conduction electron. And the empty seat, the empty spot in the valence band is called the hole. So, I talk about the thermal generation, right? So when the electron, if we ask the electron on the conduction band, are you happy? I don't know. I just remember when I took an airplane for the first time, I was nervous. Because when it landed, I shouted, wow. I was relieved. So what does that mean? Any particle has the tendency to go into the lower energy area, right? So the same thing, if I open up this water bottle and then pour out, so where will water go? It's going to go up to the ceiling? No, it's going to go up. So this go down. So this is the gravitational potential energy. So same thing in the electrical potential energy. So the upper electron, the electron at a higher energy space might not be happy. They want to go to the lower energy area. All right. Any particle has the tendency to go to the lower energy area, but there's no chance because most of the sea are occupied. But if he see one spot and then jump into that spot, then what happened to the electron? It's gone. So what happened to the seed? It's also gone. All right. So you generate a pair and also in a reversed way, the electron hole pair will die simultaneously. Okay? Get it? So vanish simultaneously. And then another electron hole pair are gone. Another, is gone. So this reverse process is called, look at the title. It's called recombination. All right? So in humans society, we have the life and death, right? So in particle world, there's also life and death. So life associated with the thermal generation. So generate electron hole pair. So electron and the hole are born. And then death associates corresponding to what? To recombination. All right? Recombination. So generation and the recombination. So now, for intrinsic semiconductor undoped, no any impurity involved in a silicon crystal. For a pure silicon crystal, intrinsic, and then there's a temperature, at the room temperature, thermal generation is going on. So if you leave in the conduction beam, you see some of the electron comes in. But also at the same time, simultaneously, some electrons goes out, right? So some comes in, so other electron goes out. So it's kind of a dynamic process. And then at thermal equilibrium, the generation rate will be equal to recombination rate. So any moment you see some electron comes in and other electron comes out, what do I try to say? The amount of electron in the conduction band will remain the constant. All right? So if there are 10 electrons on the top, it's going to be 10 holes on the bottom. So the electron carrier concentration per cubic centimeter, the N, all right? Electron carrier concentration should be equal to the whole carrier concentration for the intrinsic semiconductor. And that concentration for the intrinsic semiconductor is called the intrinsic carrier concentration, denoted Ni. All right? N equals P equals Ni. So finally, so I'm going to close this lecture. But before we close, I want to remind you, The Ni is strongly dependent on two things. Number one, temperature. When temperature goes up, Ni goes up quickly. And the second one is material. So when the lower band gap, so if lower band gap, the exponential will goes lower, right? Because it's in the denominator, so Ni will goes up quickly. All right. So strongly dependent on temperature and the band gap energy. The last one, for silicon at the room temperature, is 1.45 times 10 to the 10th power per cubic centimeter. So I guess you have to remember this. I think you have to remember this. So Ni, 10 to the 10th power per cubic centimeter. So Ni squared, 10 to the 20th power per cubic centimeter. So here's the summary, takeaway. For intrinsic semiconductors, N electron carrier concentration equals P whole carrier concentration equals Ni, which is the intrinsic carrier concentration. So in the future, you might be wondering why you teach this, the energy band. So in the future, if you want to go deep to understand more the inside, what's going on, what's the dynamics for the semiconductor device. For example, in this case, it's the p-n junction, for bias p-n junction. So we'll talk about the carrier injection, minority carrier diffusion, and thermal generation, and also electron hole recombination. So I will explain this when we study the p-n junction diode. So look forward to seeing you in the next one. Thanks for watching.